This video is about complex ions and other things that will affect solubility. So at this point, you should already be able to write KSPs for reactions and calculate their concentrations for insoluble salts. And by the end of the video, you should also be able to explain factors that affect the solubility of salts and identify and explain complex ion formation. So first, going back to kind of Le Chatelier's principle, if one of the ions in a solution at equilibrium is already dissolved in there from another species, then the equilibrium will shift to the left and form more salt, so it will precipitate out. So what we're seeing here is barium sulfate is already somewhat insoluble because it has a double-headed arrow. The barium ions can separate from the sulfate, but it also might go backwards and form the precipitate. And if you already have barium nitrate in there, that means there's already barium ions. It will form a bit less solutions because there's already those bariums in the way. So it will actually stay insoluble. Or if there's sodium sulfate or any other sulfate already present in the solution, that sulfate will force the reaction to the left, like Le Chatelier's principle says, and that means it will precipitate out barium sulfate because there's excess sulfate. So you adding in barium ions or sulfate ions from anywhere else, any other chemical, will actually make barium sulfate itself insoluble, even more insoluble than it ever was. This also happens with pH. So if you have a strong basic cation and it's in a basic solution already, that's going to make it even more insoluble, even weaker. But if it's in an acidic solution, that will actually react and rip away the ions, and it will appear to be more soluble. And substances with strong acidic anions will even be more soluble in basic ones. So they'll kind of react with the basic solution and ionize and rip apart. So the question is, which will dissolve in a acidic solution better, sodium fluoride or aluminum chloride? Well, we have to evaluate what we have here. So sodium fluoride is coming from sodium hydroxide and hydrofluoric acid, sodium hydroxide being a strong base and hydrofluoric being a weak acid. And in that case, this is a basic salt. That will dissolve better in an acidic solution, right? Because bases and acids react, and that will rip away the ions and make it more soluble. In the aluminum chloride example, that's coming from aluminum hydroxide, which is weak, and hydrochloric acid, which is strong. So this is an acidic solution. The fact that you are adding an acid to an acid is not helping things, so it will not dissolve better. In fact, it might even dissolve worse. And the third option for affecting solubility is this thing called complex ions. And they're not that tricky. Don't let the word complex fool you. It just means an ion that's charged. Normally we just have copper ions or just potassium ions. But these charged particles also get other compounds stuck to them. And so instead of it just being Cu plus 2, it's a hydrated Cu plus 2. The Cu plus 2 has 6 waters around it. And so we would write this formula as H2O6 plus 2. So there's waters attached to the copper. And the reason is because of Lewis acid-base theory that we talked about in very many videos ago, where copper has no electrons anymore, its valence is emptied. And because of that, the water can attract to it, and the oxygen's electrons can go into the copper's shell and fill it up. So the copper obtains the electrons from the oxygen's valence. And so we created this hydrated crystal, but also a Lewis acid-base pairing. So the formation of these ions actually keeps copper in the solution and makes it increase its solubility. Copper is normally not very soluble. It's a very heavy element. So usually when it's with something, it's not soluble to begin with. But if it finds these waters around it, it might actually stay in solution a little bit better is what we're saying. The value that we use to determine if this is going to happen is something called a KF or a K of formation. And it's our last K. Woohoo! And tells you that if the KF is really high, it's a very stable ion and you're going to form a lot of them, so it's actually going to make the copper more soluble than you thought. Here's another example with scandium. So scandium is plus 3. We're going to talk about just scandium for a minute and then we'll introduce the water in a moment. Normally scandium's configuration, and I know we're going way back, is argon in brackets 4s2 3d1. So hopefully you can track that with your periodic table. And scandium plus 3 occurs because it loses every valence electron. So it's just scandium plus 3 and argon in brackets. I mean, technically I'd probably go back and write what argon's configuration is, but just for the purpose of this video, that's all that's left. The valence is gone, right? In that case, if I were to talk about what's going to happen with scandium, it's pretty stable like that. But it's not very soluble. Okay, the scandium is not something we know is a strong ion of any sort. And what will happen is the s orbital from 4s and the open 3 orbitals would have been in 4p. There's 3 of them, right? And the d orbitals, 2 of them, will form 6 D2sp3 hybrid orbitals. Remember we used to talk about that? So it will start to hybridize and have these open orbitals. So instead of saying there's an s open, 3p opens that we removed all the electrons from, and all the d's that we removed all the electrons from, they actually mush together, right? And form D2sp3 6 times because it was 1s, 3 p's, and 2 d's. That's 6 letters, right? 6 orbitals. And those 6 orbitals allow water to come in. Water, the oxygen, has not only 2, but technically 4 electrons around the oxygen to fill its valence. And so 2 from that water, 2 from the second water, 2 from the third, all the way up to the 6th water. Each of them are going to give 2 electrons to those empty D2sp3 orbitals, and it allows scandium to dissolve better. The water is putting electrons back in the places that we remove them to give it to another element, right? And so that's how the complex forms. It becomes scandium with 6 waters plus 3. So it's not just scandium plus 3 anymore. That's a normal ion. It's scandium H2O6 plus 3. And that makes it stay an ion. So here's just a random list of complex ions. Things where like metal, like silver or cadmium or chromium or copper, cobalt, or whoever, is reacting with Lewis bases. Ammonia we know is a base, cyanide's basic, right? Some random basic things. They might also be waters because water can behave basically. And then they gave you Kf values for them. What they're showing you is how soluble they are. So this silver with ammonia, a complex ion, is showing a solubility of 1.7 times 10 to the 7th. That's how much better it gets at dissolving. But if there's cyanide present, that's even better at keeping the silver in solution. Silver usually precipitates out, is not very soluble, but if there's ammonia or a cyanide, or in this case thiosulfate ions in the solution already, it'll attach to them and instead stay soluble because there's still a charge at these rates. Again, cadmium, chromium, cobalt, copper, nickel, and iron are also not very soluble metals. They don't usually tend to stay as ions. But if you have these basic solutions in there, of hydroxide or thiocyanate or whatever, then they actually do help with the solubility of the ions. Notice that all these Ks are positive. That means they are good reactions that go towards the products, towards that common ion. So how do we figure out what complex ions are going to form? Like, how do I know that when cobalt reacts with chlorine, it's going to make COCl4 and not COCl2 or COCl6 and all those things? Now, in a normal reaction, I would say cobalt would probably just cling onto the 2 chlorines and become COCl2, and that would precipitate out because it's insoluble, right? But if there's a lot of chlorine present, the chlorine can act like a Lewis base and give even more electrons to the cobalt and form a complex ion to keep cobalt soluble instead of COCl2 insoluble. It might make COCl4 minus 2 soluble. So how did we know that? What you do is double the charge on the ion, so cobalt plus 2 becomes 4. That tells you how many anions you have, so 4 chlorines, right? And then figure out what your overall net charge would be. So if there's plus 2 and 4 minuses, that means you're netting a negative 2 charge, right? Another example is cobalt's plus 3, so that's why we had 6 ammonias attached to it. 3 times 2 is 6. And ammonia doesn't have a charge, so if it was cobalt plus 3 and ammonia has no charge, it stays plus 3. These things that you're attaching onto the ion are called ligands. Now, I'm not going to test you on that word, but in case you want to know it for future chemistry, they're like little arms that are coming out of the cobalt that keep it soluble. It's kind of like this, right? So the reason that works is because it's similar to the scandium example. It has open orbitals of s, p, and d orbitals, or open, no electrons in there. So the nitrogen of ammonia come in like, hey, we have electrons for you. Boom, 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 and fills all those orbitals. So here's some examples of complex ions which were not proper. That doesn't mean they won't form, but which were not proper. Ag is a plus 1 ion, so there are 2 cyanides with that. That makes sense. Each cyanide is negative 1, so if you have a plus 1 and 2 negatives, that minus does make sense. In cadmium is a plus 2 ion. There are 4 negative 1 ions because plus 2 times 2 is 4. That works out. And if you have 2 pluses and 4 minuses, minus 2 makes sense as well, so I'm good with that. Hg makes a plus 1 ion. Or plus 2 ion. In this case, I'm assuming plus 2 because 2 times 2 is 4, right? It's doubled. And so plus 2 and 4 minuses does net you a minus 2, so I'm okay with that. And last, copper. Copper can be plus 1 or plus 2. But look at how many ammonias you have. That does not work. I think that one is not a good example because it's not doubling the amount of copper's charge. There is no such thing as copper and you can also tell because ammonia has no charge that they were talking about a copper plus 2 charge and they didn't quadruple the ammonia then. In the next one, which one's more stable, then you just look at your Kf values. The higher the Kf value, the better this forms. And so I picked B because it has a 10 to the 31st power, much stronger than the 10 to the 16th. That's still soluble, but cobalt ammonium plus 3 is even more soluble. And in a complex ion formation, which substance acts like a Lewis acid, the anion or the cation? If you remember Bronsted definition, bases accept acids donate protons, then you have to just flip everything. That becomes that acids accept electrons, and so the one that's accepting electrons in all these examples is the metal part. And then some examples of the net ionic equations that we're seeing from these. If copper ions are reacting with ammonia, you're going to say it's Cu plus 2, and then ammonia, I had to quadruple the ammonia because this plus 2 is doubled, right, 4. And then just say it's going to be CuNH3 4 times, and then just make sure your charges are balanced. Plus 2 at the beginning, so plus 2 at the end. If you want to pause the video and see if you can do this yourself, that's a good idea. So zinc 1 ions means zinc is plus 1. That means I would need twice as many ammonias. And then just write it over as ZnNH3 is bonded to twice to zinc, and then plus 1 plus 1. Silver ions, which are Ag+, react with cyanide. This one's a little trickier. Ag+, we're going to double that, so we have 2 cyanides. The reason it's trickier is cyanide's minus. So you're going to write Ag cyanide 2, because you had 2 of them, but you have plus 1 and 2 minuses, so the net charge is minus, right? And last, cobalt 3 ions means it's CO plus 3. You'll need 6 ammonias, because you're doubling the charge to figure out how many. And then you just kind of smush them together, because originally the ammonia was separate, now it's stuck to the cobalt, so ammonia 6. And then plus 3 started it, so we're going to have plus 3 at the end. At this point, you should be able to explain the factors that affect a salt, like pH, common ions, or complex ions, and explain complex ion formation.